Welcome everyone. My name is Edward Wang, and this is our presentation on the Shaw Lane Reconstruction and Shaw Power Plant Renovation Project. Our company is JEQS Tech, and let's get right into the presentation. So before we begin, just a little bit of introduction on our team here at JEQS Tech. I'm currently the project manager at JEQS Tech for this project. Accompanying with me is our environmental engineer, Emily Wren, our structural engineer, Sam Morgan, our transportation engineer, Josh Benson, our pavements engineer, Jacob Carl, and our hydrology engineer, Qian Lan. So to kick things off, just a couple of design goals that we came up with in order to meet the needs and requirements of our client, such as Michigan State University and Mr. Engel, is the structural design of an academic STEM building that is supposed to be located at the northwest corner of Shaw Lane and Red Cedar Road. And a second design goal that we have is to reconstruct Shaw Lane, ranging from Chestnut Road to just east of Red Cedar Road. This will also include the assumption of the removal of North Shaw Lane according to the 2020 Campus Master Plan for MSU, which we'll go into in a later slide. This will also require the redesign and reconstruction of the existing intersection here due to the fact both westbound and eastbound Shaw Lane traffic would be located to South Shaw Lane, since North Shaw Lane currently serves westbound only traffic, and southbound South Shaw Lane currently only serves East Shaw Lane traffic. Including with this project, we'll also be designing a storm sewer system, which will be able to accommodate a 10-year storm event, and a retention basin design that will also be able to accommodate a 100-year storm event. Listening to the environmental portion of the project, we have a PCB contamination review of the site, as this used to be an old decommissioned Shaw Lane power plant, as well as conducting some research on the COVID-19 decay rate in wastewater, as this is a pretty hot topic in 2020. So a little bit of background on the project. MSU has seen an increase in STEM-related fields by 38% over the past 10 years, and recently it was found that over a third of MSU's laboratories are actually housed in facilities that are over 40 years old. Currently, all existing bike lanes, most existing bike lanes on MSU's campus are kind of discontinuous. And what I mean by that, if we look at the 2020 Campus Master Plan here to the right, we can kind of see here outlined, highlighted in the green, are sections of bike lane existing on Shaw Lane Road. So this is Shaw Lane going through the center of campus here. So the easternmost portion of Shaw Lane doesn't have bike lanes, but then it kind of has a section of bike lane for about a quarter of a mile and just ends right where we get into the center of campus here. So this project mainly focuses in this magnifying glass area is to redesign and reconstruct the South Shaw Lane to really have a continuous bike lane and to accommodate the removal of North Shaw Lane. And we really want to design our proposal to be accommodating for the 2020 Campus Master Plan, since we don't want to design anything that would need to be removed in the future, such as the removal of the parking lot over here, or even yellow where there's a proposed parking garage to be installed. So without further ado, I'm going to hand it off to Josh, and he can talk a little bit more about the transportation aspect of the project.
Thank you, Edward. My name is Joshua Benson, and I am the transportation engineer on this project. So as Edward was talking about the scope of this project, it consists of this segment of roadway from Chestnut Road to just a little bit east of Red Cedar Road. So as he was talking about, there's going to be a closure of North Shaw Lane and the conversion of all traffic heading westbound on North Shaw Lane to South Shaw Lane. So what are we going to have to do about the traffic all being converted into one roadway? So as the transportation engineer, my goal is to design a single intersection as seen in the MSU Campus Master Plan, centralized in that location instead of the current two signals that it currently has. So the redesign will consist of two-way traffic and the widening of South Shaw Lane to cut into Lot 39 to the north side of that roadway. This new intersection must be safe and follow all codes and regulations and incorporate goals of the MSU Campus Master Plan. So what is the first step I need to do to tackle this this problem. So first I'm going to have to lay out some design parameters that I will reference back to throughout my design process. So the first one is the design vehicle, and we are designing for a WB40 truck. And the second one will be the design speed, which is 30 miles per hour, and posted speed 25 miles per hour. This is important when considering sight distances and stopping sight distances for safety. Lane width for motorized vehicles, it's going to be 12 feet, and this is going to vary a little bit at the intersection. For bicycles, it's going to be 4 feet. And cross slopes, we need to design for drainage, so it's going to be 2%. And all of the curve radiuses are going to be designed appropriately for the design vehicle using the geometric constraints found in the Green Book. And max super elevation, 0.04. And what we're targeting for our level of service, which is basically like level of service is kind of a transportation term for delay, like in amount of seconds. So we're shooting for AC. So here is what I used for the modeling process. So the next step after I laid out all the design criteria is to model it in asynchronous software. So on the left, you can see the current conditions as it stands right now with the two signals, and it shows a level of service for B for both of the signals. So as a transportation engineer, I'm going to need to align with the constraints. And as you can see on the right side of the figure, it's just one single lane with a turning movement in each direction. So we kind of interpolated the traffic volumes into the right side figure to incorporate all of the traffic volumes for the proposed design. And we optimized the timing and found the best configuration to be the one on the right, showing a level service of C. And we also modeled this for a 15% increase in future traffic, and the level of service was still AC. So that is excellent. So this is the existing conditions, as we can see on this slide right here on this picture. And we are proposing to do an AutoCAD drawing and design it appropriately. So that's just a little background on what is initially at the site. So here we go. As you can see on the left figure, we have expanded to include all of Chestnut Road and included bicycle lanes and a proposed pedestrian island. And this proposed pedestrian island is for pedestrian safety, as it is a pretty, wide roadway. It's 2 lanes in each direction with a center turn lane. So there needs to be kind of a pedestrian island for pedestrian safety. And on the right-hand figure, we see the intersection geometry and the design. So we have all the radius notes and everything, all that's detailed in there, and it was designed using the ESHTO Green Book. And we have bicycle lanes traveling in each direction with a slip lane in the northwest corridor. And this pedestrian island in the northwest corridor, again, it is for pedestrian safety and optimization of level of service, as it would take a long time if it was just all roadway for the pedestrians to cross the intersection, if there was no slip lane installed there. So the bicycle lane on the northwest region right here, as you can see by the laser pointer, it is for bicycle safety. If we had it crossing just straight through, there would be a merge point of traffic, and that would be extremely dangerous for bicycles, as the oncoming vehicles are not expected to stop there. So we kind of had that align with, as the laser pointer shows, how did it align with the pedestrian sidewalk, and that was a very innovative solution for bicycle safety. So as we can see here, we have the WB40 truck coming through this slip lane, and this confirms that this can indeed pass through the lane without clipping any corners. We also did test for each of the other curve radiuses, and it ran smoothly through. So we have a nicely designed vehicle for the maximum vehicle that's going to be seen on this roadway. So this is a confirmation check. Now I will hand it off to Jacob to explain more of the pavement design aspect of this project.
Thanks, Josh. I'm Jacob Carl. I'm the pavements engineer from JEQS Tech. My responsibility is to design alternatives to pavement for the scope of this project. To start off, Michigan State University was kind enough to let us make use of their traffic data in order to find the average daily traffic for ESO calculations. Soil boring logs throughout MSU's campus allowed me to generate resilient moduluses. Due to there being a 2-foot compacted sand layer in most areas, a resilient modulus of 3,500 psi will be used. Truck factors, pay item costs, and standards were all referenced from MDOT standards based on our location and the university region, such as 12-foot wide lanes, 2% crown on red cedar and parts of South Shaw. Slab thicknesses for concrete would be a minimum of 7 inches and a minimum of 5 inches for asphalt. And an LTT bind of PG 58 to 28. South Shaw from the east end of the project to Red Cedar will have a 2.5% slope in order for water to drain to the structures. So this is how I calculated my ESOLs. I'm going to go through the table real quick. So our average daily traffic for Red Cedar was 4,153, and South Shaw had an ADT of 5,815. Percent commercial vehicles of 5% was assumed. And then our growth factor, we assumed a rate of 3% for a 20-year design, which gave us a 27 growth rate factor value. And then our truck factors, which came from the MDOT standards. For rigid pavement, we used 0.85, and for flexible, we used 0.6. Lane distribution of 0.9 and directional distribution of 0.5 due to two-way traffic. And then as you can see to the right, I calculated ESOLs for rigid pavement for Red Cedar and South Shaw, and a flexible pavement for Red Cedar and South Shaw. So there's 4 alternatives throughout the whole project. The first one was mill and fill, and we had AC overlay, a new flexible pavement, and a new rigid pavement. I was calculating an LCCA estimate for 1 lane mile for each alternative. As you can see, the PW present work, AC overlay ended up being the cheapest throughout the whole project. But since AC overlay would cause more obstacles along the way of cost and construction, we're going to choose the mill and fill alternative. The PMT value, as you can see, we can pay $16,000 or roughly $17,000 a year for the mill and fill alternative. This is a cross-section design for our pavement. So we'll start off at the top. We have 2.5 inches of 5E1 for our top course, and then we'll have 3 inches of 4E1 for our base course and leveling course. We're going to use 8 inches. We are going to use 8 inches of aggregate base and a 10-inch sand base. And then there's going to be a 4-foot bike lane as well. So this is a capital construction cost for the mill and fill alternative. Due to there being a new lane, we had to include a sub-base and aggregate base calculation. I split up the HMA values. So HMA 4E1 and 5E1 presented at the top of the table are the new quantities for paving, and then the mill and fill HMA is where we'd be paving over the existing sand bases. The table below that is the values I used for the life cycle cost analysis, and the total cost for the whole pavements would be $397,606.16. All right, I'm going to hand it off to Keelan.
Thank you, Jacob. I'm the hydrology specialist of the company. My name is Qiyuan Lan. My job is to design a new stormwater management system for the project. The new stormwater management system will be designed to meet the post-development runoff that can be reduced to the pre-development, as the new building may cause displacement at the target site. The map of the conceptual design of the site show on the next two slides, and the location of the building, retention basin, and the whole soil pipe system are clearly shown in these two slides. In general, according to the project requirements, the company needs to design a new stormwater storage system for the project area. The related design goes to ensure that the new system can accommodate 10 years of the storm event runoff to be allowed from the regulatory perspective, and the system is acceptable to the public. Meanwhile, the system has to cost effective. In order to achieve this objective, the company needs to do the hydrological analysis of the surface runoff, hydraulic analyze pipe flow, and determine the diameter of the stormwater soil pipes. The company decided to add some rain garden in the parking lot area to reduce the runoff coefficient, so that some of the rainfall will be stored rather than flow into the system. Due to the pavement and the transportation design from another specialist, the whole area was surrounded by grass except the roads and constructions. The grass is another feature that was added into the design. The soil is under the grass area, thus the stone water will infiltrate into the soil. For the standards and the regulation and rules for design, all the designs have to follow the rules of the Ingham County Drain Commissions and MSU Stormwater Design Regulations. So this is our conceptual design. We made this design in AutoCAD, and as you can see, we designed 19 subcatchments and 18 pipes and 18 inlets. This and the location of the retention pond is located in front of the new academic building as it shows in the screen, and this is the east side of our design map. The hydrology design criteria: the area of the subcatchments have to under 120 acres, and the velocity of the flow in the pipe should be in the acceptable range, that is 3 to 10 feet per second, and the runoff intensity of the installation is 5.46 inches, which is searched in the NOAA website. The soil pipe system have to match the 10-year storm water event, and the retention basin have to match the 100 years event and 24-hour period. So for the design for the solar system, the soil pipe system is a totally new system for this area because the existing pipe system may not be standard today. In this case, the existing system was ignored and not combined into our design. The whole project area being divided into several subcatchments in order to use the rational method to calculate the variables for the pipe. Meanwhile, the manual equation is also important to apply to calculate the size of the pipes and the velocity of the flow. The time of concentration used is 15 minutes for calculation. As you see in the table at right, it shows the flow rate, pipe diameters, and the flow velocities. The flow velocity have to match the acceptable ranges 3 to 10 feet per second, as I mentioned in the previous. Because the real pipe diameter is a manufacturer's pipe size, so the team decided to use the 12 and 80 inches pipes to satisfy the calculations. So for the retention basin design, retention basin is a structure used to regulate the flow of the water in or out of the area. Due to the cost-effective consideration, the company decided to use a retention basin rather than a detention basin, because the outlet design for the detention basin will improve the cost. The retention basin uses the traditional approach to hold the water and reduce the flow of the runoff by natural evaporation and infiltration. The relevant calculation for the volume of the retention basin was using the geometric calculation and design, which includes the depth, length, and width. Also, the overall flow capacity needs to be determined first in the soil pipe system to design a suitable size for the water capacity of the retention basin. As you can see in these slides, the location of the retention basin is in front of the new academic building, and the retention basin have to match the 10 years event and 24 hours period that I already mentioned. And for the diameter of the retention basin, the depth of the basin is 6.75 feet, and the volume is 167,721 cubic feet. The estimated cost for the hydrology part of the project is $529,000. The overall cost includes the soil pipes, ram, excavation, catch basin, like the inlets, and the retention basin. According to the calculation about the size of the pipe, the 8 inches and 12 inches pipe will be applied for making sure the flow capacity for the pipe is acceptable. All the price of the item will searched on the M.dot item price table, and because the green features did not account into the calculation, the total cost is supposed to be increased a little bit, and the specific detail are showing in this table. And the design is not perfect because of the limitation of the time, so that it still needs to be improved in the future, especially the soil pipe system, due to there being less information about the variables about the existing pipe system. Thus, the design is totally isolated from the old system. So the next one is our structure specialist, Sam, and here we'll talk about the structure part of the project. Thank you.
I'm Sam Morgan. I was the structural engineer on this project. So Michigan State came to us hoping to turn their old Shaw power plant into a STEM academic building. That included gutting and renovating the existing building, but also adding 2 additional structures. They wanted one structure to be specifically 80 by 200 feet and another 80 by 160 feet. They propose an L-shaped footprint, both structures being 4 stories, including a basement level, and they hoped to keep the height under 65 feet above grade. They also had their preferences and requirements on room number, room size, usage of the rooms, and average square footage of each room. So to go with their requirements, our team here wanted to meet every requirement or exceed them. We were going to handle all the permits. We made it a goal of ours to incorporate sustainability throughout the project and comply to all codes and regulations. Other goals of ours were to make a safe, practical, and aesthetically pleasing design. So here on the left, I included the structural layout showing the column spacing. The first thing to note is that we changed the footprint from what Michigan State proposed to us. We were able to keep the L-shaped footprint, but we did change the orientation to avoid a existing steam tunnel. Avoiding that steam tunnel cut down on construction cost and time. I went with a steel frame design that is brace frame, meaning pin connections. That cut down on material and incorporated sustainability, which I'll touch on later. I went with a sloped roof and made each level 12 feet high. It's also important to mention the symmetry and the structural design between the 2 structures that came in handy throughout the design and analysis. Here I just included the elevation views of the steel frame of each building. You can see the short sizes of the buildings are identical. And then you can also see the symmetry between the other two structures on the long side. Yeah, for the architectural layout, I was only able to include the first floor for a figure, but it gives you an idea of the style I incorporated. We were able to exceed every requirement as far as classroom size and room size and room amounts. I use Michigan Building Code for all the standards and specs. That includes corridor width, staircases, sizes, amounts, elevators, number of restrooms. For the structural analysis, it was time to calculate loading on the building. We included the self weight of the building, dead loads, live loads, roof live loads, wind load, and snow loads. These loads were either directly given to us by Dr. Couture, our structural engineer consultant, or calculated through ASCE manuals. There was also 3 load combinations that we applied. These work as almost factors of safety. So SAP 2000 was the software we used to analyze the loading on our building. It allowed us to make a similar structure model and then apply our calculated loads onto that model. This is where the symmetry between the structures came in handy, because we could just design one building and the loading would be similar between the two structures. So yeah, we inserted all the loads onto the building and applied them in the 3 load combinations I mentioned in the last slide. And outputted were the axial, shear, and moment forces inside all the members. From there, we were looking to find the highest of all those forces and then design using those calculated forces. Yeah, so with those design forces, we used procedures learned in CE 405 design of steel structures to get the member designs. I also use AISE manual for all the tables and charts during design. You can see here the final designs for all the members. It's important to point out that that the max forces were used in design. Specifically for columns, there was such a difference between the lower columns and the upper columns. There was subcategories made. But generally, we tried to group them all together to keep the construction simple and economical. Yeah, so like I mentioned, sustainability was a goal of ours through this project. There's a few ways that was able to be incorporated in structural design. First off was the brace frame. That just created less internal stresses within the members as compared to a moment frame. That cut down the material by up to 40%. A slope roof reduced the amount of heat needed to melt snow in the winter, being that we're in Michigan. And also just in the architectural design, incorporating like efficient windows, lighting, and equipment keeps the building sustainable throughout its lifetime. Also, sustainability could be incorporated through the materials. First off was the steel frame that we chose. The steel is local from Lansing and is expected to be 100% recycled steel. There's also materials that can be sustainable in the concrete, such as admixtures of slag and fly ash, which are byproducts from other industries, as well as if the design allows it, using recycled aggregate for the concrete, using the slabs, the basement walls, the foundations, etc. And also, there was a few cool systems that we incorporated in the design, which were the heating and cooling system, having a geothermal piping involved. That should make the heating and cooling system more efficient and reduce electricity used. And also covering the roof with solar panels. That will not be able to completely power the building, but it would reduce the carbon footprint. And with that, I'm going to pass it off to Emily, our environmental engineer.
Hi, yeah, I'm Emily Wren. I'm the environmental engineer on the project. And I primarily looked at the use of PCBs on site because it was a former power plant and PCBs were used in the transformer oil for the power plant. So I wanted to look into make sure the soil meets EPA standards on PCB contamination, and that's a limit of 50 parts per million. Anything that exceeds 50 parts per million needs to be either incinerated or sent to a landfill. That's Toxic Substance Control Act approved. And once a site undergoes remediation, it can only have a 1 part per million limit. So looking at what's happened on the site, there was a field testing performed in 1993, which found about 300 cubic yards that exceeded that 50 part per million limit. And then in 2004, that was excavated and disposed. And we get this table on the right, which was just approximations on the area and depth of the areas that were excavated and sent to the Heritage Landfill, which is in Indiana, and it is Toxic Substance Control Act approved. So we did meet all of the standards, or the excavation done in 2004-5 met all the standards set by the EPA, so the site should be ready to go for construction of a new building. Just some bonus work that we did was on looking at SARS-CoV-2 in wastewater as a potential surveillance. It's been used in the past for polio and hepatitis, this wastewater surveillance, but it's of particular interest for COVID-19 because so many cases, the patients never exhibit symptoms and might never get tested. This can also be used for testing large areas that might not be practically viable to individually medically test them, or areas where it's not economically viable. So we looked at the virus and just if it's detectable in the wastewater, and it was using qPCR analysis, which it didn't give exact concentrations of the virus, but you're able to kind of have a relative, is there high concentrations, low concentrations of the virus? And you can see that in this chart on the right. Areas where there was higher concentration or lower concentrations, obviously on your influent, pretty high concentrations, especially in your influent sludge. So then decay rates of the virus were determined to be extremely dependent on temperature. So higher temperature was faster decay rates. And that's looking at that table at the bottom. If you see this T90 column, that's the number of days it takes for 90% of the virus to decay. And so in low temperatures, like 4 or 15 degrees, it can be up to 20 to 30 days and this is in specifically untreated wastewater. So it's pretty persistent, which led us to look at if wastewater treatment process efficiently removes the virus. And in all studies, the effluent concentrations of both the sludge and the wastewater had undetectable levels of the virus. So then to test this, we wanted to specifically look at the University of Cape Town, or UCT, wastewater treatment to see if this treatment process was efficient in removing the virus. We did modeling on this using Sumo, which is an open source water treatment modeling process where you can add in your own parameters. So we added in the SARS-CoV-2 virus to watch its decay. We model it based on the East Lansing Water Resource Recovery Facility. So that's about 12.6 million gallons per day that's treated. And we inputted these decay rates found in past studies. and those were temperature dependent. So we did it based on a 20-degree temperature, which is 0.145 per day as our decay rate. And we modeled a 100-day period to guarantee that steady state conditions were reached. So we ran it once to determine what steady state conditions were, then we ran it 100 days, and those conditions were met. And you can see the steady state concentrations on the right for each of the different reactors of the UCT process. And that's starting with an influent of 100 RNA copies. And then you can see it is efficient in removing the virus. For the UCT process alone, the effluent was 0. And then the MUCT process, which is just modified UCT process, it has an extra anoxic reactor. The effluent was 0.029 RNA copies, so undetectable, but still there at extremely low concentrations. So overall, the treatment process was efficient in removing the virus out of the wastewater.
Okay, yep. Thank you, Emily. So now we're looking back at the project cost. We have the general construction costs and additional costs and fees for the overall cost of the project. Relating to the general construction costs, it's kind of broken down into a couple of sections where we have the storm water sewer system cost, the stormwater retention pond, pavements, the academic STEM building, and the transportation cost. Looking at this table, we can kind of see that the bulk of the cost comes from the academic STEM building at $98 million, that counts for about 94% of the total project cost. And coming in second, we have the transportation cost, which accounts for anything related to the reconstruction of Shaw Lane and the Red Cedar Road corridors and an intersection. That doesn't account for the pavements. That comes in about just over $1 million, accounting for 1% of the project. The additional costs and fees of the project are pretty important for the construction phase, since there's additional cost for permits, the soil erosion and sedimation cost, such as installing silt fence around the entire perimeter of the project. And then we have the inspection, design, and construction management costs all grouped together to ensure that all those are covered. And we're looking at a total project cost to come out at $104 million. And we also added on a $5 million contingency cost just in case we didn't account for all aspects of the project, coming in at a grand total at $109 million for the entire project. So on top of the construction cost, before the construction process can actually begin, a few permits are going to be required before any of this work can begin, such as the NPDES National Pollutant Discharge Permit. We also need some building permits for the building structure itself. You need a boiler permit, the building permit, electrical permit, elevators, mechanical, and plumbing. We're also going to need a soil erosion and sedimation control permit for our storm sewer network design, as well as our runoff to the retention pond. And then we're also going to need zoning permits from the city of East Lansing to ensure that everything we're building here is up to a standard with the city and MSU standards. And any paving work that happens in the city of East Lansing, public or private property, we're going to need a permit from the city just to pave the road. And we're going to need water and sewer connection, water tap permit, just in case we need to tap to any existing sewer system, stormwater sewer system, to really connect our network to the rest of the campus's network, which is part of the Ingham County storm sewer network. And then contract parking, which can be taken care of by the contractor for their necessary work requirements. The project is broken up into 3 main phases. We have the first design phase starting back in September of 2020, lasting to December of 21st of 2020, which is just about to end here. Then the construction contract will be ready for letting beginning in December 18th, going on into November 10th of 2022. So we're expecting year-round construction lasting for a full 2 years. Of course, we're planning for our construction activity to happen during the spring, fall, or winter seasons, all seasons basically, with respective work. So, any interior work can be done throughout the winter time, and exterior work should be done outside the winter seasons. And this will really provide minimal impact to the campus too, because it's kind of fenced off in its own lot where the old decommissioned Shaw power plant used to be. Phase 3, however, can't occur at the same time or as long as the same time period of phase 2, just because we will be impacting the transportation network of the campus pretty significantly, as we're going to be completely removing North Shaw Lane and realigning South Shaw Lane and redoing some of the sidewalks and driveways there as well. So this is kind of set to begin in March 1st of 2021 and ending just just after when the next fall semester starts on September 21st of 2021. We're proposing to wrap this construction up in one season, so we can do a complete closure of Shaw Lane and just kind of have the summer traffic detour around the area, as traffic conditions are going to be expected to be significantly less during the summer months compared to the fall and spring school semesters. That way we can really minimize the construction impacts to the campus and the users of MSU. So here's a draft construction schedule that we were able to put together. Pretty similar to the previous slide. We had the first phase was just the design phase, and phase 2 of construction, we can kind of see it's a 2-year phase, built into a couple stages. So we have the pre-construction tasks, such as obtaining all permits, staking lines and grades, and basically project mobilization. We also have stage 2, which includes the site clearing and utility work. That's really where we start breaking ground for the building itself. Stage 3, we have the foundation excavation work, starting to build a basement and the walls for the building. And then there we can finally start doing some interior work once we start building up the frame and the structural work of the building itself and doing the roughing process. This leads to the exterior work and the finishing work all going on into 2022. And then phase 3 kind of starts in the beginning portion of phase 2, where this is the just focusing on the Shaw Lane and Reed Cedar Road corridors, where this is going to take place between the summer months, where we have a couple stages again as well. The pre-construction stage, similar to the academic buildings construction phase. And the stage 2, we have the roadway preparation. So we got to remove any existing roadway that needs to be removed, such as the northern curb and gutter or any parking lots that we need to get, that need to be decommissioned per se. We can take a few parking stalls. And then with the roadway construction. So the goal is to really have all the paving done before the students come back for the fall semester. That way, any punch list items and cleanup work will only be left going on into September. So the roads will be open, sidewalks will be open, nothing really be impacted. Maybe we would have minor lane closures for during the non-busy hours. And I just want to thank everyone for their attention for our presentation today. That basically wraps up our presentation on the Shaw Lane and power plant renovation project. Here's the contact information if you wish to reach out to us for any questions, as questions are not currently available, but we are available by email. And thank you for your time.